to welcome Mohammad Sadegh Eshaghi to the SMaRT seminar series today. He has been a PhD candidate at physics in Leibniz University, Hannover since 2023. He completed his bachelor's degree at Amir Kabir University and his master's degree in structural engineering at KN2C University. He has worked as a programmer at the International Center for Numerical Methods in Engineering in Spain and has also been a researcher at the Institute for Structural Mechanics in Germany. He shares his research interests along in the lines of integration of deep learning and computational physics. Now, with that brief introduction, please join me in welcoming Mohammad. And with that, Mohammad, the floor is all yours.
Okay.
You can share the screen and go.
Okay, hello everyone. Thank you Sundata and SMaRT team for invitation and for hosting this webinar. Today I'll be talking about my recent work, which is neural operator, NOWS neural operator warm star for accelerating iterative solvers. In a short overview, NOWS is a hybrid framework which combine neural operator with iterative solvers to accelerate PDE simulation while preserving accuracy and stability of the classical solvers, iterative solvers. The content of my presentation is at first we discuss motivation, then we talk about methodology, and then we will discuss about a static problem. In static problem, we have considered the robustness of NOWS across different resolutions. And for neural operator part, we have used the method of Vino, variational physics informed neural networks. So I briefly discuss this method. And then I discussed the effect of physics integrations, and finally, in a static problem, we consider problems with irregular geometries. In dynamic problems, we have used a multi-head neural operator as a neural operator methods in NOWS. So I shortly discuss this method, and then we have discussed about the zero-shot super resolution property of NOWS in a dynamic problem. The motivation is that PDE is very central to modeling in physics and engineering problems, and it is fundamental for modeling complex phenomena across diverse domains. And high fidelity solvers such as finite element method or finite volume method or IGA methods are computationally intensive, and they are accurate, but their computational demands are a bottleneck for complex real-time applications. On the other hand, the neural networks or neural operators or data-driven methods are fast, but they are unreliable, especially for using them outside their training distributions, and they cannot guarantee the demanding accuracy. So we need a generalizable way to accelerate PDE solvers while preserving their accuracy and their guarantee to reach a specified accuracy. The key idea of NOWS is that we want to use a trained neural operator to provide high quality initial guesses for iterative solvers such as conjugate gradient methods. And we expect by this method, we reduce the iteration count and runtime without changing the solver structure and retain the stability and convergence guarantee of these classical solvers. Okay. Simply NOWS workflow started by training a neural operator in offline phase using sample PDE solutions or physics-informed version of neural operators. And the next step is using these neural operators to predict an initial guess. And then we can feed this initial guess into iterative solvers. And these iterative solvers works to reach to full accuracy or refine the solution, the initial guess by neural operator to achieve full accuracy. And we will show that the methodology is solver invariant, and it means it can easily integrate with different existing methods, different discretization methods such as finite elements method, finite difference, IGA, or isogeometry analysis, or finite volume methods. We have discussed these 4 methods. And here you can see a schematic overview of NOWS methodology. The left branch illustrates the data curation phase where the data are generated. If needed, we don't need data for physics-informed versions, especially for Vino. We don't need data. We can we can train the neural operator just based on physics. And the middle part describes the training phase. At first, we have a lifting operator, which converts the input to higher dimensional representation. And then we have several kernel layers with activation function. And then after these layers, we project the output to the physical space. And then if the neural operator is physics-based, we calculate PDE loss plus boundary loss. If it is not physics-informed, we need databases. And so we need databases for calculating data loss. And then finally, if the convergence criteria satisfy, the neural operator is ready. And then the right branch shows the inference phase in which parametric PDE problems are discretized using finite element method, IGA, and so on. And then the trained neural operator provide an initial guesses for the iterative solvers, and then the iterative solvers refine the solution to achieve full numerical accuracy. And we will show that using NOWS has several advantages, and it can speed up up to 90% compared to classical solver. And in some example, we show that it can reduce the iteration count by 2 or 10 times. And it preserves solver stability and convergence of the iterative solvers. And it is compatible with existing methods and existing solver infrastructure. And we can show that we will show that it is robust to mesh and geometry variations. Okay, at the first static problem, we have considered 2D Poisson equation, and we have considered robustness of nodes across different resolutions. And in this example, we integrate neural operator with finite difference method, and we have tested on different resolutions, from a coarse resolution to high fidelity resolutions. And for each one, we have tested 2,000 unseen GRF Gaussian random field samples. And we compare nodes with CG conjugate gradient baseline. Okay, for neural operator in these problems, we have used VINO, variational physics informed neural operator, which is developed in my previous works during my PhD. In this slide, I briefly discuss these methods. Actually, VINO is a framework for learning solution operators using variational principles. Starting on the left, we address the core challenges in existing methods, existing approach like PINO, physics informed neural operator, which is based on FNO, solve the S-prime form of a PDE. And this relied heavily on numerical differentiation or automatic differentiation. And as we show in our paper, this method can be unstable on fine grids, or it can be computationally expensive when, especially when they use automatic differentiations. But VINO takes a different approach. Instead of a strong form, it utilizes a variational form. And by discretization the domain, VINO can calculate differentiation and integration analytically inside each element. And we don't need to calculate the differentiation numerically. And moving to center panel, we see the mechanics of this analytical derivation. Actually, VINO breaks the domain into rectangular or other type of elements using by linear approximation function. From this element, we derive the shape function and gradient matrix. This allow us to pre-calculate the stiffness matrix and mass matrix, and finally we can calculate a loss function for each PDE. And as we can see here, at our loss function, there is no differentiation or integration, and it's just some matrix multiplication, and we don't need to numerically calculate this kind of things, and it helps us to improve the accuracy and also the speed of the method. And as you can see at the right panel, right side of the slide, we see the performance impact of NOWS. The top figure compare a standard numerical method for calculating integration and differentiation against VINO, and you can see VINO has better accuracy. But most importantly, look at the the mesh size effect plot at the bottom. As you can see here, Vino's error consistently decrease moving from or left to right by increasing the grid size. Vino's error consistently decrease and showing a kind of convergence. In contrast, the Pinot showing the Pinot method shown in green actually become unstable when you are in high fidelity meshes. Okay, it was Vino, and we use Vino for this kind of problem as a neural operator. And here you can see the iteration and runtime reduction across all resolution. We have I have shown this this figure in 2 slides. You can see from coarse grid to high fidelity grid, and this figure shows relative tolerance based on iteration count, and the orange one is just CG, and the blue one is CG initialized with NOWS. And as you can see, in all the resolution, NOWS reduce initial residual magnitude and accelerate the convergence. And also here you can see the runtime saving increase with resolutions. Actually, iteration count reduction is about 30 to 40% on coarse meshes, and near 15% on finer grids, and run time savings depending on your goal relative tolerance can be different from 90% to 23%, but because this problem is very simple, just shows the concept. It is just a proof of concept of the methods, and in more complex problem, the saving capability of NOWS will be shown more vividly. Okay, the second example is Darcy equations. In this example, we have considered effects of physics integrations. We have considered 3 conditions. The first one is data. The first one is data only, unsupervised learning of the Darcy equation. The second one is PD only, and the third one is combination of PD and data. And for this problem, Darcy equation, we use finite elements method. Actually, we integrate neural operator with finite element methods. The previous one was finite difference method. It is this one is with finite elements methods. Here you can see the effect of physics integration, and as you can see in the figures, best performance achieved by PD only model. Actually, the data plus PD in data plus PD case, we have considered weight of data and PD equally. It means we just consider the summation of data and PD loss as a final loss. But if we consider we change these hyperparameters and we consider different ratio of these losses, definitely the result can be change, but for the comparison, we keep this weight equals 1. Here you can see as the number of modes, number of Fourier modes, or equally network parameters increase, the test error decrease for PD only training, but increase for data and PD plus data models. And it shows that considering physics can be very helpful, and actually it can avoid to overfitting. And also in Darcy equation, we have considered different preconditioner in CG solvers. One of other parameter which we can change is the preconditioner in CG solvers. We have considered 5 conditions. The first one is without preconditioner. The second one is Jacobi, SSOR. The next one ICC, and the last one is incomplete LU methods, which can here we want to see the effect of NOWS using different preconditioner in CG solvers. And the result, and you can see the result in this slide. In this slide, actually the colors without hash is for the color with hatches is for NOWS, and the color without hatches is when we use just CG solvers without NOWS. And you can see for all of the preconditional methods and for all relative tolerance, NOWS can reduce the time run time. And here we show the relative tolerance based on iterations, and for the same problems, and you can see the same concept. And for different preconditional methods, you can see NOWS can reduce the iteration count of the simulation. The next problem which NOWS can perform very better and show the importance of use of using NOWS very vividly is irregular geometries, which is a bit more challenging. We have we have considered here plate with arbitrary voids. Actually, the input of the neural operator is geometry of the problems, geometry of the plate, and the output is solution field, which can be displacement field or stress field. And here we use IGA solver as a discretization method. Actually, we integrate NOWS with IGA, isogeometric analysis. Okay, here you can see the result for this problem with irregular geometry. The first actually left top figure show relative residuals versus iteration count for the conjugate gradient solver and for NOWS. As you can see, NOWS consistently reduce the initial residual and reduce the number of iteration which require to reach a target tolerance. Actually, this plot is shown the result for 15 test sample, and as you can see, it can reduce the iteration count about 10 times, and it can save a lot of times in simulation. The second figure show time to reach the tolerance, and as you can see, for example, for the residual tolerance equals 10 in power of -6, NOWS can save the runtime about 87%, which is very important, very useful. And the left panel shows a sample of the problems, and as you can see, NOWS results has very good accuracy, and we can preserve the accuracy and convergence guarantee of iterative solvers. Okay, the next problems is dynamic problems. For dynamic problems, at first we considered for proof of concept, we considered the Berger's equations. Actually, Berger's equations is a fundamental PDE used to model various physical phenomena involving fluid motion or gas dynamics and so on. And it includes a nonlinear convection part and diffusion part. It is a nonlinear PDE, and so it is important to test it by NOWS. And at the left side, you can see the spatiotemporal evolution of the solution field for a representative test sample in the Berger's equations. The first one is exact reference, and at the middle, you can see the NOWS results, and finally, you can see the error panel. And for neural operator part, we have used the MHNO model or multi-head neural operator, which is another method we have developed during my PhD. Actually, the concept of MHNO is that in MHNO, we replace the single global projection operator in existing methods like FNO with a set of time-specific projection networks. And we introduce a temporal coupling networks between these projection networks. Actually, between different time steps. And this enables MHNO to explicit stepwise temporal dynamics within a neural operator frameworks. Actually, here you can see the MHNO can receive actually the initial condition of the problems and project it into the high dimensional space, and we have a Fourier backends. We have several Fourier backends, and then after Fourier backends, we have some step-aware branches with different convolutional layer, and these different these different branches is connected with another networks, which denoted here by H. And finally, we have all of time step in one single path. And as we shown in our paper, advantages of MHNO is that by a single forward path, we can predict all time steps. And it shows the result shows that MHNO avoids error accumulation, which we have seen in previous works. And we have shown that it is more scalable than existing Fourier neural operator methods, for especially for line horizon problems. Okay. Here you can see the result of using NOWS for Berger's equations. We have compared the runtime distribution of CG methods and NOWS. As you can see, the runtime can reduce for all of the samples of our data sets when we use NOWS. And here you can see all of our initial condition in test data set. And we can see that NOWS can reduce about 15% of time step from about 10 seconds to 5 seconds in this simple problem. And here we have considered another a bit more challenging dynamic problems. We have actually considered a SMaRT problem, which is a coupled problem, which can include these three PDEs. Actually, it is incompressible Navier-Stokes with buoyancy, and actually a smoke density advected and coupled with velocity field. And actually, in this problems, we have in the traditional method, the pressure projection, the last equations solved via CG solvers. And for this problem, we test the zero-shot super resolution property of NOWS. Actually, we trained the neural operator on a coarse grid. We trained the neural operator on 64 times 64 grid, and apply it directly to a fine grid, which is here is 256 by 256 without retraining the neural operators. And the result is very interesting. You can see without NOWS, for one sample, it is just for one sample. Without NOWS, the solver time is about 300 seconds. But when we use NOWS, the solver times become about less than 100 seconds. And you can see the convergence number in a different time step for both of the case is 150, which shows that for all of the time step we reach the convergence criteria. And also you can see that the total iteration in NOWS has been decreased dramatically from about 70,000 to just 17,000, and it shows that it confirms mesh resolution invariance and generalization capacity of NOWS, because at this example, we trained, as I said, we trained the neural operator on just a coarse grid, and I use it directly in a fine grid solver as an input, as an initial guess for fine grid solvers. Yes. And it is my presentation. It was my presentation. Thank you for your attention, and I am here for your potential for your questions.
Thank you, Mohammed, for this amazing presentation. I'll open the floor for questions.
Can you see my still my presentation?
No, I see a dark screen.
Okay.
Okay, maybe I can start. I have a couple of questions from your presentation.
Yes.
Yeah. Do you want to share your screen again, maybe?
Yeah. Yes. Can you see it now?
No.
How about now? Actually, I share it, but I don't know what is the problem.
Oh no, I don't see it. Never mind. I think we can just discuss. So I was wondering, like these hybrid methods, they are gaining popularity primarily because of their ability to extrapolate or like scale to higher dimensions, etc. So have you checked checked your methods for extrapolation?
Actually, if I
Yeah, we do see your screen now.
okay, good. For example, in these problems, we use it in fine grid. Actually, these grid problems we have not seen in the in our database. Database was just on this coarse grid, but we use it in fine grid. It can be considered as a extrapolation, but no, I have not checked it or checked this ability.
Like
Yeah,
what
for
I
example,
meant
yeah,
was like an initial condition drawn from a different distribution, or maybe like going longer in time.
yes. No, actually, I have not considered this one, but yeah, it would be interesting, yeah, to see how it works, yeah. But I have not seen. I have not checked it actually.
Yeah, and I had a few more questions. The geometry example was amazing. So wanted to know when you're testing, when you're presenting these testing results, are these geometry fixed number of geometries that the network has seen, or you're testing it on a different geometry?
No, I tested in different geometry. Actually, you can see some samples of our test data set here. And actually, the geometry has some limitation. But for example, the geometry is inside of the rectangular domain. It is 5 by 5, but the void can be everywhere in the domain, and it can randomly actually randomly generated by some actually methods, but it can be different. It's not just some fixed irregular geometries.
So your training geometries and your testing geometries were different.
Yes.
I see. That's interesting.
Yeah.
And because because for these geometries, did you have to go finer in discretization to represent the shapes?
Actually, yes, we have used 200 by 200 mesh size. Our mesh is 200 by 200 actually.
I see. I see. Yeah, I was wondering because these geometries are like intricate, so you might need finer discretization.
Yeah.
So following on the same point, you mentioned that as you go higher in discretization with the Fourier neural operator, you often face, you often see overfitting issues with things
Uh,
running higher in error, like the error increases. So I was wondering, have you kept the number of modes across all of them, all the discretization the same, or like and number of Fourier modes as well as the number of Fourier modules?
okay. What is the variable here?
So for that for moving across discretization, like the discretization density,
Mhm.
when you are running your Fourier neural operator, are you keeping the number of modes same based on the lowest discretization, or are you changing that also?
Actually, do you mean in this example which I show here, or
No, the
which I?
previous one, Vino, Pino, and
Okay, okay. Here, actually, everything, yes, everything is the same. Everything is the same for this result. We just changed the mesh size.
Mhm.
And yes, you can see that in Vino we have this convergence behavior, but in Pino you see this instability.
Yeah, I guess this is primarily because of the variational form that you are using, because
Yeah.
that has lower order derivative. Pinot is on the strong form.
Yeah, actually, one reason can be this one, and but I think the most important one is that actually we don't really calculate the derivatives analytically. We just use a pre-calculated or loss function, which is actually we pre-calculate a loss function for a specific PD, and we use this loss function. In this loss function, there is no derivatives actually. So there is no this instability we can see in Pinot.
I see. I see. I see. Okay. Wow.
When you use this for example bilinear approximation function, it can be other approximation function, but for example when you use this bilinear approximation function, you can calculate all the loss function analytically inside each domain, you know.
Yeah. Yeah.
So you don't need to be worried about calculating this kind of things numerically, which produce instability, which cost or which are costly when you have a mesh a bigger mesh size, you know.
Mm-hmm. I agree. And the other question which I have is like, I mean, it's kind of coming from a person who hasn't like really gone into the depth of this paper. I was wondering, like, if we have to handle adaptivity in meshes, how do you think we can do it with this method?
Or actually, what do you mean by
Because
additivity?
we are going to change the resolution, let's say at every time step, um, and
Okay.
the physics will also change over time, like as the solution evolves. So how do you think that if we are doing it only through physics informed,
Mm-hmm.
mm, because I saw in one of them you do have standalone physics informed.
Yes.
Any suggestions, guidance on that?
Actually, for a static problem, we have seen that the pure physics informed version can perform better than data-driven version.
Mm-hmm.
But for actually for mesh actually, mesh property, you said, yeah, I think it can be very helpful when you can train on a coarse mesh and use it on a fine grid mesh, which, for example, in real problems, it is very important that you need a fine grid actually, but you cannot train neural networks on a fine grid. You can
Mm-hmm.
train the neural networks on a coarse grid, which is very uh, simpler and it is very faster. And then you use this neural operator directly to a to a real problem. You see?
Yeah, but with adaptivity, you won't have a uniform mesh because I believe that with FNO, this is a major challenge that you might face. Super resolution is a great idea, but
Yeah.
that's on a uniform grid after all.
Okay. No, I didn't consider this property. Yeah.
Yeah, no worries. I was thinking more in those directions,
Yeah.
so probably I thought of
Yeah. I
asking you.
think it would be interesting actually to
Great.
work on it.
Let's see if we have questions from the audience.
Okay.
Yes, Divya, go ahead.
Uh, Hi, Mohammed.
Hi.
Thank you for the nice presentation.
Welcome.
So I had a question regarding the multi-head neural operator.
Okay.
Yeah. So uh, can you go to that slide? Yeah.
This one. Yeah.
Yeah. So the second, after the Fourier backend, you have a multi-head neural network kind of architecture for every time step, right?
Yes. For
So
different time step.
yeah, so I had like two questions here.
Mm.
First is what is the intuitive I mean the reasoning behind using that multi-head? And then
Mm-hmm.
second is if we have a single head for every possible time step, then if we have a problem where the discretization or where the DT that we're operating is less, then this network size can grow pretty quickly, right? If you have more number of time steps to process.
Yeah, actually, I see your question.
Yeah.
Yeah. Actually, the intuitive of the this model is that we have used this model for some phase field problems. In phase field problems, we have actually different behavior in different time step of the problems. So we need uh, an architect, a model which can capture this different behavior. And
Mm.
we show that using just one projection projection layer is not enough for capturing this different behavior. So we have used these different branches for different time step, but actually it can be the size of these heads, the number of these heads can be different based on our problems and our needs. Actually, it can is the hyperparameters of this method actually. And for the second question is very important, but the point is that exactly it is we can reduce the number of parameters using MHNO, especially when the number of time step is high, because when for example, I am comparing this structure with FNO 3D. In FNO 3D, the number of time step one dimension is for time, so the number of time step is exactly in your is in actually is in your architecture of your model. So
Right.
when you have different when you have a very long time step, this Fourier backend of your model is become very massive, and
Right.
the number of time step is become very high. But we in this model we keep the Fourier backend to light, and use different branches, which is very small uh, uh, layer, the number of parameters in this step or branches is very smaller than this Fourier backend. So increasing this part is very better than actually the Fourier backend. So we have shown that this model, this method can handle the problem with fewer parameters actually.
Right, right. I see, I see. So, I mean, to like make it more simple, can we, I mean, think of this model as we are trying to learn an operator where we are trying to independently learn a mapping from the initial condition to every time step separately and not in one go. Like not one global operator, but multiple operators.
Yeah, exactly.
Uh,
And on the other hand, for example, when you use FNO 2D, for FNO 2D, you need to run the neural operator for each time step, and it means for example, when you have 1,000 time step or 100 time step, you need to run FNO 100 times, and
right,
it makes the time of inference time very high, and also
right,
the training process of this one is very challenging and produce actually zero gradient, and it's not so easy to train these networks.
right, right, right. Yeah, yeah, that is true.
Yeah.
Yeah. All right, thank you.
Do we have more questions for Mohammed? Okay. If not, thank you so much, Mohammed, for taking your time to tune in today. So
Thank you very much.
it was a pleasure talking to you. Thank you.
Thank
And
you
to
very much
all,
for
to
giving me
everyone
this opportunity.
else, we'll see you. We have one more question from Vivek. Maybe we can take that. We have 4 minutes. Vivek, you want to go ahead and ask your question? Oh, he just logged off. Not sure what happened. Anyways, thank you so much, Ehsan, and thank you everyone. We'll see you again next week.
See you. Goodbye.